The biological science topic being taught is how an owl uses sound source localization for its predatory methods. It can find prey when they're on the move. The applied science topic being taught is the velocity equals distance over time relationship.
The biological science topic being portrayed is sound localization, which is the process of locating a sound based on the distance and direction of the perceived sound. Owls use this process to determine the origin of a sound in three-dimensional space in order to aid itself when hunting at night or in low-light conditions. An owl's ears are located apart from each other so that one ear is above and in front of the other, which is demonstrated in our concept.
To demonstrate our applied science, which is the velocity equals distance over time relationship, we've utilized one speaker and two different microphones. Each microphone represents an owl's ear. To find the prey's position in the XY plane, we measure the amount of time it takes for the sound to be received by each microphone, and then knowing the distance between the ears and the amount of time and the difference in time between the ears, we can calculate the X value. We can then rotate the one ear down and back, which allows us to calculate the distance in the Z plane.
The final product will be able to break apart into three sections. This is so the entire product can fit into the storage bins used by the Academy of Natural Sciences. The first section holds the displays, LED lights, buttons, and lever. The middle section contains the owl with the two built-in microphones. The end section will hold the speaker, which will run along a cutout path. Now on the right we can see the displays, which will display the time that it takes for the sound to reach each ear. The button in the middle will be pressed to have the speaker emit the sound. The lever will allow the owl to rotate so the ears can come closer to the sound produced. The LED lights will turn on depending on the closeness of the sound emitted. Now from our final product, we have four crucial functionalities that need to be tested. The first, we need to have the prototype be capable of identifying which ear receives the sound first, have the displays display the correct time, and have the LED lights emit the light on the closest side. This covers the need to teach a STEM lesson. The owl head, represented as a crossframe in the prototype, will need to be able to rotate. This will cover the need to have user inputs. The calculation of the amount of time it takes for the sound to be emitted and then received by the microphone must be correct. This will cover the need to teach a STEM lesson accurately and have accurate inputs. Finally, the ears should be capable of being repositioned to three different positions. This will cover the need for student interactivity. To cover these crucial functionalities, the prototype will have a crossframe in place of the owl head with microphones attached on each end on repositionable pieces. The LED lights, displays, buttons, and lever will all be placed on the first section and tested, and the speaker will run along a cutout path on the end section.
For future work, we would like to include the ability to adjust the speaker height with a push-pull solenoid, and we would like to have a model owl covering the microphones. In addition, we'd like to have an improved display panel that displays 8 digits instead of 4, and an improved microphone and Arduino, because we currently lose some values based on calculation time.
Our total available project budget was $250. We only spent $210, giving us around $40 left, and we saved money mainly by using low-cost vendors such as McMaster-Carr for our lumber supplies, Lowe's for lumber, and then Ada Fruit and SparkFun for our electronics. Stakeholder needs and target specifications were met with the final prototype and confirmed with evaluation via performance in experiments 1 through 3. Results from experiment 1 indicated proper function of the speakers, microphones, LEDs, and connections to the Arduino board. Experiment 2 indicated that the operator could precisely control the direction of the owl head, and a practice demonstration was conducted to make sure that the product could be separated into its individual components and that they could all fit into a container and moved easily by the user. The optimal performance of the LCD readout displays and distance from the speaker to the microphones was indicated in experiments 3 and 4. The Academy of Natural Sciences and other educational institutions could benefit from this product being manufactured by EduRob, since a production version of our design would maintain the proven functionality with a more robust frame and cleaner physical appearance. For example, the material would be changed from plywood to plastic, which would still provide enough room in the upright portion of the product and allow graphics on the front of the product to appear more lifelike and like a real-life owl.
This is our project to show sound source localization as found in owls, and to demonstrate that we have 2 microphones here to represent the 2 ears of the owl. And what's going to happen is a fixed point, prey is going to make a noise through our speaker system, and the ears are going to pick that up, and each ear will pick up a different time, and those times will be represented on the displays. So when the system makes noise, our 2 times are displayed, the distance between the ears will let us know how far and where the prey is located, as an owl would do. For the second phase of our demonstration, we're going to be showing predatory methods in an owl finding, targeting a moving prey. And to do this, as the prey moves across the face of the owl, an LED system will demonstrate which ear is closest to the prey, which is how the owl would know which side of the owl the prey is on.
Okay, so to validate the fact that the first stage of our sound source localization is calculating the right numbers, we found the time it takes for the shortest distance from the microphone to the speaker and the most extreme or farthest distance from the microphone to the speaker. And at a distance of 869.95 millimeters, we found that it takes 4,819 nanoseconds for the sound to reach the microphone, and then at the other extreme we have 517.52 millimeters. It would, at that distance, take 7,940 nanoseconds, and these are the readings that you see on the screen.